Hello friends, today we are going to see how to print all the diagonal elements in a binary tree. So let's see the example. So for printing diagonal elements in this binary tree, we have to mark the diagonal distance for each node in this tree. So we represent diagonal distance with notation D. So D is equal to diagonal distance. And here are two rules for writing or for marking the diagonal distance. Let's see the rules. So the first rule is D increments by 1, that is D is equal to D plus 1 only for left child. So only for left child in the binary tree, the D, that is diagonal distance, increments by 1. And the second rule is for every right child, D remains same as of parent. So D is equal to D of parent for every right child. So let's see how to apply these rules. So for root, the diagonal distance is 0. This is the basic distance, that is because it is a root, the distance is 0. Now the left child of A is B. So the value, that is the diagonal distance, will increment by 1 because it is the left child. And the right child of A is C. So D will remain same, that is 0 as of parent. Let's go ahead. So B's left child is D. So the diagonal distance will increment. So D will become 2. 1 plus 1, 2. And the right child of B is E. So D will remain same as of parent. So D is equal to 1 for E, because it is same as the parent diagonal distance. Now for C, the left child is F, so the diagonal distance will be 1 because the parent diagonal distance is 0, so 0 plus 1 is 1. And for right child, D will remain same. So this is how we mark the diagonal distance. Now let's find out the diagonals. Now the diagonal distances which are same fall in the same diagonal. So D is equal to 0, D is equal to 0 and D is equal to 0. They form a diagonal. So the first diagonal is ACG. Now the second diagonal is the distances which are 1. So D is equal to 1, D is equal to 1 and D is equal to 1. So these three nodes. So B, E and F. And the third diagonal is for D is equal to 2. So only one node is there with distance 2. So that is the third diagonal. So these are the three diagonals in this binary tree. Here I would like to mention that this is the method which works for every binary tree, and this method always gives the perfect answer. I am telling you this because on some websites on internet, the method of marking these inclined lines is given. So marking these inclined lines, this method works only for small binary trees, but for large binary trees like this method will never work because it is very complicated to mark inclined lines in this larger tree, and this may give you wrong answers most of the times. So you always have to use the distance of diagonal, the method of diagonal distance for marking the diagonal elements. So let's see the larger example. Yes, D is equal to 0. The left child, yes, d is equal to 1. Right child, d is equal to 0. Now henceforth I will only write the distance. So here d is equal to 1. So for d it is 2. For e it is same. Here it will increment by 1. Here it will remain same. Again increment by 1. Remain same. Increment by 1. So distance will be 4. So no right child here. Here it will remain same as it is the right child. Increment by 1. Remain same. Increment by 1 here. Remain same. Increment by 1 for this node. Then increment by 1. So it will become 2. Here it will remain same. Increment by 1 as it is the left child. Remains, here I have to increment by 1. Increment by 1. And here it will remain same. Here it will remain same. This right child, so it will remain same. So we have marked all the distances. Now let's find out the diagonals. So first, all d is equal to zeros. A, C, G, M, R. Now all d is equal to 1s. So B, E, F. So all d is equal to 1s are B, E, then F, K, L and Q. Now all d is equal to 2s. D is equal to 2. B, I, J, B, I, J, M, V and P, this T and P. I should write PT because that will follow the order as it is the parent and this is the child. Now D is equal to 3. H, U, S, these are the 3 nodes with D is equal to 3 and D is equal to 4. This that is N. So N. So here are the diagonals. These are the 5 diagonals in this binary tree. So let's see the faster method to mark these distances. I will tell you a shortcut to mark these distances. So first, root is 0. Now all the right child series of the node, mark them of the same distance. This is the shortcut. Remember, all the right child series. So A's right child is C, 0, C's right child is G, 0, G's right child is M, 0, M's right child is R, that is 0. Let's go ahead. Now you know that this is the 0th diagonal. For simplicity, I will say that as the 0th diagonal. So the 0th diagonal is ACGMR. So let's go ahead. Now the left children of the elements in the 0th diagonal should be marked as 1, that is 0 plus 1. So the left child of A is B, so the distance will be 1. Go next. Now the left child of C is F, so it will be marked as 1. The left child of G is L, will be marked as 1. M doesn't have left child and R does not have left child. Now when we mark 1, then do the same process as we did in this case. That is, mark the right child series as the same distance. So D is equal to 1, we have marked it. Now mark the right child series. So 1, its right child is E, so that is same distance 1. Then its right child is K, so the same distance. Now for this node its right child is the Q, so the same distance. Check whether any node is left. No. So we have covered all the nodes with distance 1. So our first diagonal will be now BEK FLQ. This is the first diagonal. Now let's go ahead. Now all the left children of the elements in the first diagonal, let's mark them as distance 2. So left child of B is D, distance 2. Left child of E is J, so the distance is 2. Then left child of F is not present, L is present, distance is 2. Okay. Now any other child is left. For Q there is no left child, so leave it. Yes. So these are the 3 nodes we have marked. And the next step is check for the right child series of those nodes. So the right child series for D is I, so the same distance, M, same distance, V, same distance. And right child series of P is T, so same distance. Check whether any, for J there is no right child, so no node is left. Yes, so this is our second diagonal. Let's mark it DIMV JPP. Now let's go ahead. So mark the left children of nodes in the second diagonal. So left child of D is H, so distance will be 3. Then left child of P is S, so distance will be 3. Yes, these are the 2 nodes. So the third diagonal, check for the right child series. They don't have right child, so it is H and S. And now let's go for the left children of nodes in the third diagonal. So the left child is N, so that is the fourth diagonal. Yes, so this is the shortcut. Now let's see the algorithm for writing the program. So we are going to execute this algorithm on this binary tree so that you can understand perfectly. Now for the algorithm we are going to use this queue. So let's see the code now. So the first step is NQ root and NQ null. So the root of the binary tree is A. We have NQ'd it and we have to NQ null. So as we go further you will understand why we have NQ'd this null. Now let's go ahead. While Q is not empty, P is equal to DQ. So we have to DQ from the Q. So we get A when we DQ. So P pointer P will point to A. Now if P equal to null, which is not the case here because P is pointing to a node, that is A. So we go in the next block of code, that is a while loop. So while P is not equal to null, yes, print P. So we print this A and we check whether A has a left child or not. That is, if P points left. So if it has the left child, then we NQ that left child. So let's check whether A has left child. Yes, it has. So we have to NQ that left child. So we are NQing B. Okay. Now the next line is P is equal to P points right. So in the shortcut I have told you that we have to traverse through the right child series, which is represented by this line. P is equal to P points right. So go to the right. Yes, now P will point here to C. Now again in this while loop we will check whether it is null. No, it is not null, so we print P. So we print C. Yes. So I will tell you the meaning now. This means that we have to traverse the right child series. We have to traverse the right child series, and while traversing the right child series, for every node we have to check whether that node has left child or not, and if it has the left child, then we have to enqueue that left child. Let's follow the procedure. So C has a left child? Yes, it has. So enqueue it and go to the right. So P will go to G now. So whether G has left child? No. So just print G and go to the right child. Whether L has left child? Yes, it has. So enqueue the left child, print L and go to the right. Whether N has left child? No. So just print N and go to the right. Right is null. So there is no node to the right. So when there is no node to the right, when P becomes null, so P is equal to null, so we come out of this while loop. We come out. And as there is nothing here, we go to the starting of the outer while loop here. And then we dequeue from the queue. When we dequeue from the queue, we get null. So if P equal to null, this condition is satisfied, because now when we dequeued we got null. So it has the condition has been satisfied, and then we enqueue another null. At the end you will understand the purpose of enqueuing another null, but now I have to tell you that when P is equal to null, this means that this block of code tells us that the first diagonal is over and we are moving to the next diagonal. So the first diagonal is over when P is equal to null, and we are moving to the next diagonal, and when we move to the next diagonal we have to enqueue an extra null in the queue. You will understand it when we reach to the end why we are enqueuing null. Now we dequeue again. So inside this if we dequeue again and we check whether that is null or not. So we dequeue again. So again we dequeue, so we get B. So if B is null, no, it is not null. So we don't have any problem. We move to the next block of code here. So again the same procedure while P is not equal to null. Let's follow the procedure. Our P is pointing to B now. P is pointing to B. Yes. Check whether it has a left child. Yes, it has the left child. So enqueue the left child, then print B and move to the right child of B. Whether E has the left child? No. Whether E has the right child? No. So we just print E, and as the right child is null, we come out of this while loop and we again go to the beginning of the outer while loop and we dequeue. So when we dequeue, we get F, and again we follow the same procedure. So we get F, and now we check whether it has left child. Yes, it has. So we NQ that and we move to the right of F and we write F here, and the right child is K, so we write K. We check whether it has left child. No. It has right child. No. So it is null. So we come out of this while loop and we again move to the beginning. Okay. Now here again we DQ. So now when we DQ we get M. M is DQ'd. So let's go to M. Yes, M is here. P is pointing to M now. Previously it was pointing to P. I forgot to write here P. So now it is pointing to M. So write M, and it doesn't have left and right child. So the next step is DQ. So when we DQ we get null, and when we get null we come to know that diagonal is over and we move to the next diagonal. So when we DQ and when we get null, we come to know that diagonal is over and move to the next diagonal, and moving to the next diagonal, while moving to the next diagonal we NQ null, extra null. So now you will understand why we NQ'd this null. Okay, this is the tracing of the next diagonal. So this null will tell you that the diagonal of these nodes is over. In short, what we are doing, the nodes which are coming in the queue, we are just printing that node and their right child series. Their right child series. I will say that their right series. Now BFM and their respective right series. D and J, their right series we will print. So just blindly you can say DJ, and what is the right series of DJ? D's right series is I and J's right series is null. So this is your third diagonal. This simple it is. And whether D has left child? Yes, it has. So just NQ that left child. As we have printed D and J, we have DQ'd them. And when we DQ next, we will find the null. And we have printed DJI. When we encounter null, we understand that this diagonal is over. Okay? And we NQ another null. So we NQ another null here. Now again P is equal to DQ. So we DQ H. So H is DQ'd. Check, H has left child? No. Whether it has right child? No. So we just print H, that is our fourth diagonal. H is our fourth diagonal, and after printing H we move to the right side, we get null. So we went out and now we DQ. So when we DQ we get this null, and when we get this null we understand that the diagonal is over and we NQ another null. Here this important condition you will understand, we again DQ, so we get null again. So now P is null, and if P equal to null we break. This means that all the diagonals are over. Means when two continuous null are inserted in the queue, this means that our algorithm is now coming out of the function, which means that our all diagonals are over and we have printed all the diagonals. Yes, so this is how the algorithm works, and you can get the full code on github.com/Vivekananda
44. Just check the code there and you can use the code for your work. Thank you.
Hey friends, please subscribe to my channel as I post algorithm videos every day. And if you want a video on any particular topic, then please mention in the comment below. Thank you.